Okay, so let's have another example. Okay, so this will be our sixth video for the topic shear and moment diagram. And this is actually the fourth example. Okay, so please consider these beams. Okay, as you can see, the difference between, from part 5 is that this will be a 2-degree curve. Okay, so that is the only difference. So see, it's just similar to what we have on our third example, or from the part 5, but somehow this is not a 1-degree curve or a triangular load, but a 2-degree curve. Okay, in which it can be set as uh, a curve which has to the power square, which is the power is squared. Okay, x squared, like that. This curve can be represented as, let us say, y is equal to ax squared. Okay, so it means it has a power of 2. So it is a second degree curve. So when it is an n degree curve, it is in the form of y is to a to the power x times n to the power of n, where a is a constant. Okay, so just like that. So that is how we produce your second and n degree curve respectively. Okay, so just like also for 0-degree curve. Okay, this is a 0-degree curve, and this is a 1-degree curve. Okay, so I hope you will understand now. Okay, so this is actually a to the power of x0, or simply a. So this is a 0-degree curve, and this is a 1 first degree. Okay, so I hope you will understand now what do I mean by first degree, 0-degree, second degree, and nth degree. So that is how it is. Okay, so now just like the previous examples, we will solve first the reactions. Okay, so we have summation of forces at x is equal to 0. Let us say the right is positive. So we have ax. So since there is no other horizontal forces, we can see, so ax is 0. Then we have summation of forces y is equal to 0, upward as positive. Okay, so we have two vertical upward reactions, ay and by. So it's positive, and then we have negative 75 since it's downward. And then another thing, since we have this formula, let me remind you that for any n value, okay, so nth degree curve, okay, so please remember this. Okay, please remember this. Its area is equivalent to 1 times n plus 1 times BH. Okay, so the B here is 4.5. The n is 2, so 1 over 3. 2 plus 1 is 3 times B is 4.5, and your H is 16. So that is your area, so that it will become kilonewton. Everyone, AY, BY, kilonewton, and this will be in kilonewton. So AY plus BY minus 75 minus 24 equals 0. So we have AY plus BY equals 99. Okay, and then we have another thing is we can have summation of moments. Okay, so let us choose what is the most favorable. Okay, so let us say summation of moment at A. Okay, Nevertheless, you can also use B. Okay? 0. Let us say counterclockwise as positive. Okay. So since we sum up moments at A, so your A will be the fixed, will be the steady point or the fulcrum. Okay, so and the rest will make the body rotate. Okay, so since, okay, so this is your steady point or fulcrum, this 75 kilonewton will tend to rotate clockwise. So this is negative 75. And since this is a vertical force, we need to find its perpendicular distance from A, or that will be its moment arm. So it's, since this is vertical, so its moment arm is 2 from A. And then we go to this point. Okay, so please do remember, okay, so relative to the right corner, if this is n for any n degree curve, any n degree curve, its center of gravity is located over B. Okay, this is B, let us say this is B over n plus 2. Okay, so since this is a second degree curve, your CG from the right support is B over 4. So 4.5 divide 4 is 1.125. Okay, so this is also applicable to triangular. Since the triangular n is equal to 1, so B over 3. And for 0 degree curve, or those okay, this is a first degree curve, so this will became B over 3. And for 0 degree curve, this 0 degree, this will become B over 2. Okay, so that is the formula, but base it from the right side. Okay, from the bigger, since this is increasing, the right side is here, B over 4. So that is it. Okay, so please do remember this formula, because I will erase this one. Okay, so later, so we have the area, which is 1/3 4.5 times 16 times B over 4, which is 1.125. Okay, and then your By relative to A, it will become okay, so it will act relative to A. This is, it will rotate, this By will rotate as counterclockwise, so it's positive. So positive, okay, its moment arm is 2 plus 2 plus 4.5 is equals to 8.5 times By equals 0. Okay, so we can compute now the value of your By. Okay, so we have, okay, plus 75 is, okay, and 1/3 4.5 times 16. I know this is not 1.125 only, so we have 8.5, the whole length. Okay, the whole length, which is 8.5 because relative to A. So 8.5 minus 1.125. So this is, okay. So therefore we can compute your by. Okay. So 38.471, okay, kilonewton. So since this is positive, so our assumed um, uh, direction is correct, and then we resubstitute in this formula. So we have AY plus BY is equal to 99, okay? So you transpose, you substitute 38.471 equals 99. So we can get your value, okay? 99 minus answer. Okay, we have 60.529 kilonewton upward, okay? Okay. So now we can, okay, I will erase some of these things so that um, we can construct our shear and moment diagram. Okay. AX equals 0, AY is 60.529 kilonewton, and BY is 38.471 kilonewton. Okay, we project this in order to get the shear and moment equation. And then we have this. Okay. We have Vx and Mx. Okay, or the P. Okay, so this is the zero area and this is your X. It is increasing. Okay, it is from left to right. Okay, so I will erase this one so that we can construct the shear and moment shear and moment equations. Okay, since this is a video, so you can repeat the portions in which is unclear to you so that you will understand better, or you can understand better. Okay. Okay. Shear and moment equations. Okay, so we begin at this point. Okay, so I'm sorry. So we need to divide it into sections. Okay, section 1, section 2, and section 3. Okay, from this, okay, so every time there is a change in loading, so you put section. Okay, so there is actually 3 times in which, 2 times in which the loading changes. So therefore, there is n plus 1 of that changes the number of your the number of your sections. Section 1, 2, and 3. Okay. Section 1 is from point A to the point load, and then from that point load to the beginning of your um, this this distributed loading, okay, ununiformly distributed loading, this is 2, and that for the whole length of your distributed loading, that is the section 3. Okay, so how are we going to tackle that? Okay, so at section 1. We begin at section 1. Section 1, which is x is equal to 0 to x is equal to 2. So we have this. Any random x, okay? So since this x may exist between 0 and 2, so this 75 kilonewton will not exist yet, okay? So this is AY equals 60.529. Then we have 0 for AX. Okay? We only need the vertical component for your shear and moment diagram. So AX, you just neglect it. So we have V here is equivalent to 60.529. Equivalent to AY. So this is your shear. And your moment is 60.529 X. Okay? Please take note that if you integrate the shear, you will get the moment or the equation of the moment. And then we have at section 2, which x is equal to 2, 2x is equal to 4. Okay, so we have this again. But somehow after 2 meters, there is 75 kilonewton loading. And then this is your whole duration of x. Okay, so your shear here is 60.529 upward, and then this downward force is 75. Okay, so please do remember these formulas. Okay, for point load, you have negative P, and then moment is negative P times X minus A. Okay, so since, okay, from that point, okay, so we have, so that is negative. So since this is upward force, this is positive. So your B is negative 14.471. So that is the formula of your shear at section 2. And your moment is 60.529 X minus 75 times X minus 2. And the A here is 2. Okay? From this formula. Remember this formula from our part 1. P times X minus A. Where A is the distance from your leftmost support to the center of your load. Okay? So if this load is upward instead of downward, so this is positive and this will be positive. Okay? So since the A here in 75 is located 2 meters from the support, so you multiply it by X minus 2, in which the A is 2. But here, your AY is upward, 60.529. So its distance from your support is 0 because it is located as support. So you multiply it directly by X. Okay? This A can be also 0. Okay, so that one. So this is your M. 60.529 X minus 75 times X minus 2. Okay? So we go to section 3. Where X is equal to 4, to X is equal to 8.5. Okay. So this is not that easy anymore, okay? It is 2 degrees, 16 kilonewton meter. Okay. So we have 2, 2, and then we have X here. We have AY is 60.529. Okay, AX equals 0. Okay, so we have V is equivalent to, okay, let's conserve space. V is equal to 60.529 minus 75 since it's downward, and then we have this equation. Okay, for 2 degree curve. Okay, so we have negative W times X minus A cubed over 3L squared for shear, and negative WX minus A4 over 12L squared. Okay, so we have, since it's shear, So the W here is 16. And then the length here is, the L here is actually the length of your distributed load. So here, it is 4.5. So negative 16 times X, its A is obviously from left support is 4. X minus 4 to the power of 3 over 3. The L here is, so the L here is 4.5 squared. Okay? So therefore, we can get the V, which is negative 14.471 minus 4.5 squared times 3 is 60.75. X minus 4 cube. So this is your shear equation. And your moment is 60.529 X and then minus 75 times X. Okay? Minus 4 minus the W. Okay? Use this equation, negative W, which is 16. And then 12L squared. 12 times 4.5 squared. Okay, so I just put it directly here. So 243. Okay, this is 216 over 243. X minus 4 to the power of 4. So this is your M. Okay, so we will check if these formulas are correct. So if it is not correct, you will not get 0 in both ends of your shear and moment diagram. Okay, so from here, our initial value of 6529, it will increase the support from 0 to 60.529. Okay, this is 60.529 from x equals to 0 to 2. Okay, so this is consistent, 60.529. And then we have a short, okay, at x equals to 2 to x equals to 4, it became suddenly negative 14.471. So let us assume that the negative 14.471 is here, okay, and then until here, okay. So there is a downward movement, okay, direct downward, because of this 75 kilonewton force, okay, it acts downward. And then, at section 3, we have this formula, okay? So, see, at x equals to 4, it will become negative 14.471. Also, obviously in that formulas. Either when you use this formula or this formula, you get negative 14.471. So what if its value, if x is 8.5, so we can get the shear at this point. Okay, so negative 14.471 minus 16 divided 60.75 times 8.5 minus 4 to the power of 3. Okay, so we get 38.471. So since this is a 2-degree curve, in the moment diagram, in the shear diagram, it will become 3 degrees. You add 1. So this is 2 degrees. You add 1, it became 3 degrees. And since, okay, in decreasing order. Okay. So this is a 3-degree curve here. This is your, okay, it should be lower than this. So here, maybe we can write it like this. Okay, so this is negative 38.471. And lastly, since there is an upward force, there is an upward force at point B, at these supports. So negative 38.471 plus 38.471 is 0. Okay, so we get 0, 0 here. So this is your shear diagram. So what about our moment? Okay, so here we got M equals 60.529 at section 1. Okay, so in order to lessen our efforts, we can directly substitute the beginning and end. Okay, so when x equals to 0, we multiply it, then your M is 0 also. Here, 0. And then if your M is equals to the end, at the end point, which is 2 meters, your M is 60.529 times 2 is 121.058. Here, let's put it here, 121.058 kilonewton meter. And then, at section 2, okay, M is equal to 60.529x minus 75 times x minus 2. So when x equals to 2, obviously this will become 0, null. So the same as this. So 121.058. But when x equals to 4, we substitute. Minus 75 times. So we have 92.116. Okay, so since this is a 0 degree curve, this is became 1 degree. Okay, this is also 1 degree but negative since it is a negative area. So it is 1 degree curve or a constant downward. Okay, 92.116 kilonewton meter. Okay, so since this is a 3rd degree curve, this will be a 4th degree curve downward. Okay, so let's make it higher. So it will look closer to reality. Okay, so we substitute if 8.5 here. So if it is 0, then it is valid. Okay, let's try. 60.529 times 8.5 minus 75 times 8.5 minus 4 minus 16 divided 243 times 8.5 minus 4 to the power of 4. Okay. So this should be x minus 2, sorry, because, okay, this should be x minus 2 class. Okay, so we have seen our error. Okay, here, because it starts, its A is x minus 2, okay? Okay, negative 3.5 times 10 to the negative 3. So since we have round off the value of your reactions, so do not expect that it will become 0 also. Okay, there will be a little, very little value. It is 0.003, negative 0.0035. Okay, so this is since this is very small value, so we can deduce that this is just a round off error. So we have 0. Okay, so this is not a straight line but a curve. Okay, like that. So this is a 4th degree curve. Okay, so this 4th degree curve is, okay, so it would be better like that. Okay, so this is a 4th degree curve. So this is how we construct our shear and moment diagrams. Okay, so please take note that this shear and moment equation, by using the shear and moment equation, you can actually find the moment within this point, not just on x equals 2, x equals 4, and x equals 8.5, but any point in between within this. For example, this point, x equals 1 meter. So you can find its shear and moment when x is equal to 1. And when x is equal to 3, for example, since it is located in between section 2, so you use these formulas. When x is equal to 6, since it is between x equals 4 to x equals 8.5, it is within section 3, so you can use these following formulas to find the value of shear and moment at that specific point, depending on what section they are, okay? So that is our fourth example, and this is actually our sixth video in this lesson, shear and moment diagrams, okay? So I hope we understand each other, okay? So till next time.